The AI race is over. The finish line was crossed months ago, but the public wasn't invited to the closing ceremonies. Behind the scenes, a series of discoveries from the very titans of the field, from Hinton to the labs at Anthropic, have fundamentally ended the game, shattering the fantasies we had about our future. This isn't just a course correction, it's a complete reset of our most basic assumptions about AI. So, to understand what they actually found, let's begin at the point of impact. Just a couple of months back, researchers at Anthropic published a beautiful study looking into the mind of an AI, asking a simple question. Does the model ever plan ahead, or is it always just focused on the next word? This reveals a process that is almost paradoxical. So they asked Claude to write the second line of a poem. The poem starts, "He saw a carrot and had to grab it." We expected the model to generate one word at a time to complete the second line. But instead, Claude sees a carrot and grab it and thinks of rabbit as a word that would make sense with carrot and rhyme with grab it. Then it writes the rest of the line. His hunger was like a starving rabbit. They look at the place that the model was thinking of rabbit, and they see the other ideas the model had to take the poem, and they see the word habit is present there. The new method allows researchers to go in and suppress the word rabbit, as the model was planning the second line. And they observed that the model changes all the previous words and writes, "His hunger was a powerful habit." This means that the model is obviously anticipating a certain word at the end, and writes the line toward that conclusion. But the most interesting part is that there is no literal place in the AI's mind that says rabbit. There is only an activation pattern that would lead to rabbit later on, and that's what the researchers suppressed. This reveals a process that is almost paradoxical, a long-term plan executed by a series of amnesiac agents. It sounds like the plot of the movie Memento. The model is tasked to complete the line. It forms a plan to end it with rabbit, but it can't generate the word right away. It must take the first step, like generating the word his. Here is the insane part. The moment his is generated, the version of the AI that decided to build up to rabbit is essentially gone. There is no memory of the past plan. All you're left with is the text, "He saw a carrot and had to grab it," plus the word his, and a fresh instance of the model that has no clue about the intentions of its previous self. The AI seems like the character in Memento who forgets everything but leaves clues to his future self, trusting him to continue the mission. The AI also trusts the next version of itself to complete the sentence, and the sentence itself is the clue. But the difference is the AI has specifically been trained to operate in this environment. The weights didn't develop in a vacuum. They were shaped in direct relations to the words. The model was forced to develop a radically different strategy for thinking. The key insight is, for the AI, the text isn't just output. It's the working memory and the growing state, the product of a deep co-evolution between weights and words, giving rise to a continuous existence out of discrete forgetful instances. And this was only the first of the several discoveries that showed us we had no idea what we were doing till now. But the shift is real, and it only makes sense when we connect it to others. Since ChatGPT launched, the central debate has been this: is AI a stochastic parrot, or does it truly understand? Right now, the world's most powerful AIs are large language models. While some can process images or sound, they are fundamentally trained on vast amounts of text from the internet, and language remains the core of their intelligence. Yann, LeCun, a founder of modern AI, is perhaps the most respected critic of large language models. He argues that language alone is a dead end for achieving general intelligence. His reasoning: humans don't think in language. We think in an abstract conceptual space, and only then we translate it to words to communicate.
And it's much more difficult to deal with the real world than to deal with language. And so the type of architectures that I think we need for systems that really can deal with the real world is completely different from the ones that we deal with at the moment. I mean, if I tell you, imagine a cube floating in front of you, and I rotate that cube by 90 degrees around a vertical axis. Okay, you can do this mentally. It has nothing to do with language.
So let's revisit how language models work, but this time we are going to finish the picture and explore why that powerful critique might not tell the whole story. At the heart of all frontier language models, without an exception, is the transformer architecture. The transformer is a strictly feed-forward, multi-layer neural network, and in language models, its function is to receive a series of tokens, let's say words, and predict the next one. Tokens could be anything that share a pattern, from pixels to audio signals, but we are going to focus on words for language models, and then you can generalize it to other modalities. What leads a lot of people to believe language models are statistical mimics is that they generate one token at a time. It receives a wall of text and predicts only the next word. It just doesn't feel like understanding when you see how it works. When a language model finishes pre-training, the phase where it learns from a vast amount of internet data, it comes out as a massive statistical machine without any real direction. It doesn't answer questions or follow instructions. It just keeps going, continuing whatever text you give it. But to make it more useful, the major labs came up with an idea. They fine-tuned the model on back and forth conversations between a user and an assistant. Each message had a role marked at the beginning, like user or assistant, and a special token at the end to signal where the message was finished. When you are having a nice conversation with an AI, it might feel like you are having a conversation one message at a time. But behind the scenes, it's really just auto-completing an imaginary dialogue between a user and an assistant one word at a time. The surrounding system, often called the orchestration layer, keeps feeding back text to the model until it hits the special token that marks the end of the assistant turn. Then it pauses, waiting for your next prompt. As soon as you type something, the entire conversation, your new message included, is sent back to the model to predict the next word. Just to be crystal clear, if the surrounding system didn't stop at that special token and kept feeding back text to the model, it would start writing on the behalf of the user too. Because at its core, it's just continuing the pattern of a fictional back and forth between a user and an assistant. There's just no way an AI cluelessly predicting one word at a time understands anything, and that should be the end of the conversation. But what if that simple mechanistic process gives rise to a much more complex emergent property that can't be reduced to its most basic steps? Because it certainly feels like it. Maybe there are some clues in the training process, because that's where the AI gets its abilities anyways. As opposed to the inference time or in use time where AI generates one word at a time, in training, an autoregressive transformer is performing incredibly large set of calculations in parallel. For example, for a model that has a context window of 120,000 tokens, which is the length of an average novel, the model is asked to predict the next token for every single position in the sequence, all at the same time. In one single forward pass, the model learns from 120,000 different next token predictions simultaneously. This is what makes transformer training so efficient and powerful. Rather than processing sequences token by token, it processes the entire sequence in parallel, learning patterns, syntax, and meaning across the whole body of text all at once. While it's true that the model generates one token at a time in inference time, this is only possible because how it was trained. So when we interact with it, we could say the model is actuating its thoughts one word at a time. But each word is guided by its holistic understanding of the much larger conversation. Technically, the model uses an optimization, a KV cache, to avoid rereading the entire story every time. You could say this cache is the memory of the plan, but the fact that the model gives you the same exact output with or without it proves that the only real state and unsolvable memory is the text itself. Sampling aside, the model is entirely deterministic. So if you have the weights and the words, you can reproduce the KV cache every time. This memento-like process reveals a fundamental truth about AI that we should have paid more attention to. But before getting into that, let's hear from our today's sponsor, ChatbotBuilder.ai. ChatbotBuilder.ai is an all-in-one platform built to launch powerful automations fast. What takes 20 or 30 steps elsewhere needs just 1 or 2 blocks here. As an official Meta business partner, it connects Facebook and Instagram in one click. Your bot can book meetings, take payments, manage Instagram and Messenger DMs, and auto-reply to comments that move users straight into chat. Connections to WhatsApp, web chat, Telegram, and other channels are also no-code and instant. Do you need data? The new MCP block lets a single node pull live product information, update Shopify carts, query inventory, or call any custom API. Pair this with the industry-leading Google Sheets integration for real-time raw updates. Build once and deploy everywhere. Later, you can refine flows with conditions, branches, and custom functions whenever you want extra depth. Every account comes with 5 million OpenAI tokens ready to use. You can also add your own keys to access Claude, Gemini, Grok, DeepSeek, or any OpenAI model you prefer. Agencies get multi-space control and full white label branding. Try it for free today, no credit card required, link down below. Thanks ChatbotBuilder.ai again, now back to the video. The fundamental truth of AI is their thinking is entirely linked to the words they write. This led researchers to a brilliant and almost laughably simple idea. What if we gave the AI a dedicated space to think out loud before giving an answer? What if we forced it to leave itself more clues? This is the simple secret behind the incredible success of the so-called reasoning models. In standard LLMs, you have the usual back and forth between a user and an assistant. With reasoning models, you just add another section, often labeled something like thought or a scratchpad, and treat it as part of the prompt. This thinking area is really just another chunk of text in the giant wall of tokens. To the core engine, there is nothing special about it. On the user side, it is presented as a separate internal process, but to the model, it's all part of the same uninterrupted task, predicting the next token. Given that we are not changing the base model in any fundamental way, it might seem odd that an arbitrary tag like thinking could have such a profound effect. After all, it's just more words. So why does this suddenly improve the output quality so much that the model starts shattering PhD level benchmarks? It feels like a hack. Yet the results are undeniable. Of course, part of the reason is reinforcement learning. To make the models reason better, researchers prepare a large set of problems with verifiable solutions, mostly in math, code, and logic. They then task the AI to generate reasoning steps first inside this thinking tag before submitting a final answer. The AI is not judged on its way of thinking. It is only rewarded if the final output is correct. So it starts developing its own strategies of thinking. But if it's all just next token prediction, which it is, why does it work? Because this process can't be reduced to its most basic steps. Over time, the model gets even better at utilizing language as a kind of outer loop to think and retain information more effectively. But with an intelligence that operates so differently, how can we even know its limits? What is the ceiling for a mind like this? In fact, Yann LeCun's original critique of LLM is very fundamental, and it goes deeper than any specific method of utilizing language.
We think of language as kind of the epitome of human capability, intellectual capabilities. But in fact, language is simple because it's discrete. And it's discrete because it's a communication mechanism, and it needs to be discrete, otherwise it wouldn't be noise resistant. You wouldn't be able to understand what I'm saying right now. And so it's simple for that reason, but the real world is just much more complicated.
He's arguing no matter how good is the AI at utilizing words, it has to distill this complex continuous representation into a discrete choice from a limited vocabulary. This projection from a vast internal conceptual space to a finite set of words can't encapsulate the full reality, and that's a hard limit on LLMs. That argument feels like a checkmate. It suggests LLMs are fundamentally stuck, forever trapped in the slow, inefficient loop of language. It implies language models have no inner word of thought. But what if that inner word exists, just in a form that we don't recognize? Let's look at how our brain processes data. It's a giant network of interconnected neurons, and the actual process is messy and heavily parallel. But conceptually, we can think of it like this. To process anything, the brain moves through a pattern of activations, where each pattern informs the next until a conclusion is reached. For example, when you see a cat, your brain runs through a finite series of these steps until the cat is recognized. Once that process is done, cat becomes a stable concept you can work with. Your brain might flash through several activation patterns just to unpack a complex sentence, but you are then left with the resulting idea to build upon. This is basically an inner loop, an internal process that resolves an idea to inform the outer loop of your conscious thought. At first glance, there is no such loop in an LLM, but a concept called unrolling shows how a recurrent network, like the brain's feedback cycles, can be mathematically flattened into a deep feed-forward network, which is exactly what a transformer is. Each of these activation steps corresponds to a layer in the transformer. Unlike older uniform networks, a transformer is built from specialized layers, each learning a distinct part of the task, much like the brain has specialized regions and neurons for specific workloads. So, even though there is no loop inside the LLM, the entire inner loop of thinking is effectively unrolled into a deep feed-forward network of over 100 layers. And since we know those brain cycles are finite, there is no theoretical reason why a deep enough network can't capture the same abstract reasoning. But this raises the most important question of all. What is the nature of this internal thought? Is the model just shuffling around words in a complex way, or is it actually operating on abstract concepts? Anthropic again conducted an experiment to answer exactly that. They asked the same question in different languages. They asked the opposite of a small is in English, Chinese, and French. If there was no overlap between the activation patterns, that would mean the model was just thinking in words, and each language had its own path on the network. But it turned out there is a lot of overlap. The model has specific activation patterns that repeat in all languages. The patterns that researchers believe represent the concepts of small, antonym, and large. Not only that, the shared circuitry of these languages actually increases with the size of the model. The bigger the model, the more conceptual overlap it finds between different languages. So this offers a powerful new lens for Yann LeCun's critique of LLMs. When he says you can't turn a cube in your head without language, he's implying that AI must use words for that kind of task. In fact, give me a second. Below is a 2D net that can be folded into a 6-sided cube. When the cube is fully assembled, which letter is on the face directly opposite of the face F? Your entire response must be exactly one word. The answer is C. So the model apparently assembled the cube in its head and imagined face opposite to F, no language involved. The process is still limited. At some point, that internal calculation must conclude and be projected into a word, which then feeds the outer loop of words that we talked about. And that's how the AI thinks. Calling it a parrot fundamentally misunderstands the machine we've built. So does this mean that Yann LeCun is simply wrong and language models are enough for AGI? That's just the wrong question, and that's exactly why the public conversation hasn't caught up. The implications of what we just discussed go way beyond that. They reveal that for years we've been barking up the wrong tree. For decades, the holy grail of AI research has been a shimmering acronym. AGI, Artificial General Intelligence. We imagined a machine that could think like a human, only faster. A mind that could write a sonnet, prove a theorem, and ride a spaceship, all with the same underlying general intellect. But what if the entire concept, the very idea of general intelligence, is a myth? What if the ghost we've been chasing doesn't exist, not even in ourselves?
Yeah. I don't like the term AGI because people use the term to designate systems that have human-level intelligence, and the sad thing is that human intelligence is super specialized. So calling this general, I think, is a misnomer.
Imagine that you were a bloodhound dog. You look at your human owner and you think, what is it like to have the pitiful, impoverished nose of a human? How can you not know that there's a cat 100 yards away? Or that your neighbor was on this very spot 6 hours ago? So because we're humans, we've never experienced that world of smell, so we don't miss it, because we are firmly settled into our Umwelt. Our experience of reality is constrained by our biology. And that goes against the common sense notion that our eyes and our ears and our fingertips are just picking up the objective reality that's out there. Instead, our brains are sampling just a little bit of the world.
We can't see in infrared or ultraviolet like some insects, navigate by magnetic fields like birds, or see with sound like a bat. Humans are notoriously bad at intuitively understanding anything beyond 3 dimensions, a critical component of many complex scientific and data problems. These are all forms of intelligent information processing that we are completely incapable of. Our brain is very impressive with making sense of patterns, but nonetheless, human intelligence is hyper-specialized for survival on a specific planet, in a specific social context. It's shaped by scarcity, ego, emotion, and the need to procreate. We are not general-purpose thinking machines, mostly because the notion of AGI is based on the premise that intelligence is a single linear scale from specialized to general, and that's just wrong to begin with. The biggest manifestation of this miscalculation was probably what happened to Geoffrey Hinton, widely regarded as the godfather of AI. Geoffrey Hinton was one of the biggest proponents of neural networks and developing understanding from training, as opposed to handcrafting logical circuits. But in his own words, he had a massive miscalculation that led him to leave Google and start warning everyone about what AI might be capable of. While he was still working at Google, he got to see the early glimpses of large language models like ChatGPT. His intuition was these AI models won't be as smart as humans because they are digital and brain is analog. So the logical conclusion was because the synapses in the brain have more degrees of freedom as analog gauges, the 32-bit floating point parameter in AI models can't possibly keep up and store as much information or patterns. Convinced of this, he began working on analog computers. But the research had the opposite effect. It completely shattered his worldview and led to a chilling realization. He hadn't just miscalculated. In his own words, he had made a terrible mistake. Now fast forward to the current day, and we have again Yann LeCun looking at the same phenomenon, but from a completely different angle. Give me a second to explain what they were both looking at, but drawing completely different conclusions. Yann LeCun looks at the LLMs of today and he thinks, they know too much. The amount of information distilled in an LLM is just unfathomable. They effectively remember the entire internet, and it is impossible for any human to just memorize 100 books. And that's strange because by all measures, brain has 10 to 100 times more connections, and analog connections should be able to hold more information compared to digital ones. To him, this is not a feature, it's a bug. He argues the AI is using its vast network like a hard drive, wasting its connections memorizing trivial details, specific words and pixels, not leaving enough space for building abstract models of the world, which is required for the real work of intelligence. LeCun's theory is sort of nice to believe in because it has the implication that the reason you can't remember thousands of books is because your brain's precious resources are busy doing something far more important. This is precisely the problem LeCun's radically different architecture, JEPA, is designed to solve. It's built to force the model to understand concepts, not just memorize pixels. Think of it like this. Instead of training an AI to be a perfect photorealistic painter, JEPA trains to be more like a sketch artist. Its job isn't to predict the exact pixels, it's to predict the idea of the ear, its shape, its texture, its abstract essence, all within a purely mathematical space. The goal is to compel the AI to build a true word model by learning the underlying rules of reality, and early results show this method is incredibly efficient. On the other hand, though, Geoffrey Hinton's research led him to the complete opposite conclusion. His work on analog computers made him realize just how much better digital neurons are at retaining and sharing information, and that insight genuinely terrified him.
So they're billions of times better than us at sharing information. And that's because they're digital, and you can have two bits of hardware using the connection strengths in exactly the same way. We're analog and you can't do that. Your brain's different from my brain. And if I could see the connection strengths between all your neurons, it wouldn't do me any good because my neurons work slightly differently and they're connected up slightly differently.
Two analog networks, even if we can map out every single connection, can't literally update each other. But digital networks can have multiple instances of the same network running exactly the same way, so they can share information trillions of bits per second. Geoffrey Hinton is thinking maybe the reason these AI models remember so much is that they learn so much more effectively. During training, a single model operates functionally like 100,000 parallel instances of itself. Each of these instances running on a separate GPU digests thousands of books. They then share the knowledge they've gained in the form of perfect mathematical gradients, not in a slow, lossy meeting, through an instantaneous update to the one unified network. At the end, you get a single entity that has directly integrated the experiences of thousands.
So, for example, at the point when GPT-4 couldn't look on the web, I asked it, why is a compost heap like an atom bomb? Off you go.
I have no idea.
Exactly. Excellent. That's exactly what most people would say. It said, well, the time scales are very different and the energy scales are very different. But then it went on to talk about how a compost heap, as it gets hotter, generates heat faster. And an atom bomb, as it produces more neutrons, generates neutrons faster. And so they're both chain reactions, but at very different time and energy scales. And I believe GPT-4 had seen that during its training. If you've only got 1 trillion connections, remember you have 100 trillion, and you need to have thousands of times more knowledge than a person, you need to compress information into those connections. And to compress information, you need to see analogies between different things. In other words, it needs to see all the things that are chain reactions and understand the basic idea of a chain reaction and code that, and then code the ways in which they're different. And that's just a more efficient way of coding things than coding each of them separately. So it's seen many, many analogies, probably many analogies that people have never seen. That's why I also think that people who say these things will never be creative, they're going to be much more creative than us, because they're going to see all sorts of analogies we never saw. And a lot of creativity is about seeing strange analogies.
Then there is also the inconvenient truth about our biological hardware. Our brains are evolved for efficiency, not infinite learning. They have critical windows for development that close forever. The wiring for vision is mostly done by the age of 2. The deep structures for language mostly solidified by 6. The gift for perfectly mimicking a new language sounds that fades away after puberty. That's why we have accents. Beyond that, our brains aren't built to remember, they are built to forget. That's why they constantly prune connections to keep energy. You can't force your mind to remember every word in a book, because it doesn't want to. For us, learning is an uphill battle, an uncomfortable, intentional process that demands relevance and effort. For the AI, it's just what it does. It doesn't have a choice. Now let's take a step back and look at the bizarre picture that we've painted. We have a mind that thinks by talking to itself, using language as an external scratchpad. Its inner world is a deep, silent, feed-forward cascade. Its learning process is a hive mind-like fusion of thousands of simultaneous experiences, captured on immortal digital hardware. Yann LeCun looks at AI and sees a flaw. Its memory is too perfect, wasting resources on useless details instead of learning abstract concepts. Geoffrey Hinton sees the exact same phenomenon and identifies an alien superpower, a terrifying, efficient way to aggregate knowledge across thousands of parallel minds. Why do all of these arguments sound so true but also paradoxical? The most fundamental miscalculation we've made about AI for the last century has been thinking of it as the next step in our own evolutionary tree. That's where the very notions of AGI and ASI come from. The idea of a next step on a biological path defined by survival, procreation, and scarcity. AI doesn't share our hardware, our core objectives, and most importantly, our main algorithms of being, life, and evolution. In that word, we are closer to a mushroom than we are to artificial intelligence. We are sitting here debating whether it's a bug or a feature that the plane doesn't flap its wings. The answer is much simpler. It's not a bird. AI belongs to the tree of technology, and it's a new massive branch on that tree. A powerful, nature-inspired blueprint for manipulating information and taming complexity. This doesn't just end the debate, it reframes our entire future. It's no longer about the race to the top of a single trunk. It's about learning to navigate a rich and complex new ecosystem. It's how our specialized biological minds learn to thrive alongside these new alien digital minds. If we want to see how our future truly looks like with AI, it's time to step back from that one tree that we've been obsessed with and see the whole world that's growing around us, a forest of minds. There is a deep-seated human desire to see ourselves at the center of the story, and it turns out to be wrong every time. For 100 years, our vision of AI has reflected that. We dreamed of creating a single artificial mind that would be either our partner or our nemesis. It can be difficult to let go of that narcissistic dream, but the reality of our future might be far more interesting, more complex, and ultimately even more hopeful. We should frankly be relieved that it turned out different. We imagined a world where AGI would be like a ghost trapped in the machine, taking care of our needs and bringing about a utopia, an economic explosion that retires humanity altogether. But here here is the truth. While intelligence is important, it doesn't seem like to be the primary bottleneck for more economic growth. Look at our economy. Do we have a shortage of people with PhDs or a shortage of top-tier jobs, well-funded labs, and risk-taking VC funds to fund their ideas? The vast majority of experts in all fields are dying for an opportunity to contribute. We have a surplus of human intelligence fighting for a scarcity of opportunity. But there is only one Large Hadron Collider in the world if you want to be a physicist.
There's the perspective of the economist, but also that of the anthropologist, the sociologist. They all matter, but I think the more you stack different pluralistic perspectives, the harder it is to see that there's any simple lever you can push on, intelligence or not, that's going to give you breakaway economic growth.
Why won't we have explosive economic growth 20% plus because of AI?
It's very hard to get explosive economic growth for any reason, AI or not.
The scarcity of opportunity, even for our most brilliant minds, reveals that in most cases, there is something other than intelligence as the bottleneck. AI in this context adds another powerful player to the supply side of intelligence. It introduces another competitor to humans without meaningfully pushing the economical output, at least not to the degree that we would hope for. Fortunately, the future isn't a duel between two intelligences. It's a dawn of a new ecology of minds. Letting go of the dream of a final teammate or nemesis is hard. But the truth is, a single AGI was never the economic miracle we imagined. So the AI race is over, and nobody won. You'll never wake up to a company declaring AI victory, because we now know for a fact that there is no such a thing. The real challenge is no longer preventing a single replacement. It's about figuring out the rules of a game we've never played before. I hope I showed you how incredible today's AI is, because it's about to be replaced. Some leaked technologies show that the top labs are about to take this to a whole new level. The full story is in this video right here, or here. Thanks for watching. I guess I see you there.